Hi everybody, welcome to the next lecture on basics of video technology, this time about psycho-optics. So first let's go back into the history for different levels of abstraction of images or scenery. So first we had this mapping of three-dimensional objects onto two-dimensional screens or surfaces, for instance, very early, for instance, on cave paintings, right? So there should be a T. So that was already kind of a projection, 3D to 2P, to 2D. Then the next is the decomposition into pixels. For instance, photocells and early transmissions of video were done in parallel transmission, like all the pixels transmitted in parallel. But because that is kind of unpractical, there was this decomposition into temporal successive pixels, so parallel to serial, right? We had this sampling and then parallel to serial transmission for images and also for moving images, black and white, TV for instance, and later color. Yeah, so here the psychophysics. So we start with a real world, which is 3D. Then we have a lens here, and we would like to have a 3D representation in the brain, right? So the brain needs to know what's going on in the real world, right, to make a model of the world. But what we have on the eye is a two-dimensional surface of the retina, right? So there's first a mapping of the 3D world onto this 2D world, and then the brain tries to estimate the real 3D scenery out of it. So because there is a lot of information lost in this representation, the brain tries to reconstruct the lost information from cues it gets from this 2D projection. Right. So this is how the eye is doing it. So here you can see, here's the lens. From the right hand side you can see the light coming into the eye, and then the lens focuses those parallel beams of light into one point. Right? And if those parallel lights come from a slightly different direction, then this is projected to a different point. So that's a projection on the retina. So you can see a little bit more detail about it. So here again is the lens. Here you have the retina. And here you can see the visual nerve, the nerve fiber going to the brain. And you can see here is actually a little hole in the retina, and this is because those nerves actually pass through the retina and then are distributed on top of the retina. So those nerves are actually transparent and they come from the top of the retina, and that's why it needs a hole to go back into the brain. And that's basically because that's how the eye evolved as kind of a externalization of brain fibers. So that's why it needs this hole. That's, for instance, very different to some species of squid, for instance. For them, the eye developed separately, and then they had the nerves coming from the back, and hence they don't need to have this hole, which is actually the blind spot that we have in our eye. Yeah, and here we can also see there are muscles here to the lens, and those muscles are for the autofocus. So when we focus near or far, then basically we need those muscles in the eye to focus depending on the distance. So that's kind of our autofocus here. Right. So this is basically a projection. And mathematically, we can actually describe this projection as a matrix multiplication of this 3D scenery with 3D coordinates. And basically, we are losing one of those coordinates to create the projection on a 2D surface. So this can most easily be represented by this pinhole camera. So this is a closed box, and then we have a tiny hole on one side, and that means that all the light that's coming inside must pass through this hole. And because light is always traveling on straight lines, that means we get this upside down projection inside this pinhole camera. And yeah, basically we get this projection of an entire 3D scenery which is in front of it. Right. So mathematically we can describe this by a projection matrix P, which we can see here next. So this is our matrix P, and you can see it actually contains an additional dimension, the W, which is useful for including a translation or shift, and it's also useful to defining a projection plane. Right. So here we have the world coordinates x, y, and z. For every point we have this triplet of coordinates. Then there is this additional coordinate which we call w. And then output is just two coordinates, x and y, for the projection plane. And again, some helper variable w. And then we need to choose those coefficients p according to the properties of the camera. So here this factor w can be now used for a projection. So in this way. So if we have x and y and some w here, then this describes the same point as x divided by w, y divided by w, and 1. So it's basically a projection on the plane z equals 1, which can be seen here in this next example. So here we have a very simple projection matrix, which is basically consisting of this diagonal of 1s, and then the last column is just 0. And then this also shows that the capital W doesn't really matter here because it's all multiplied to 0. So what this does is the output x is the same as input x from the 3D world, then the input y is the same, the output y is the same as input y, but now z is getting mapped to the w, this helper variable. And now we saw we have this definition that this is the same as dividing it by w, and here the w becomes z. So basically the projection then is then x, y results from the 3D world coordinates x and y divided by z, the distance from the camera. Right? And that means the further an object is away from the camera, the smaller it appears on the display. And this is how we would expect it from a lens, right? When something is far away, then it should appear smaller. Yeah, and yeah, so this is a very simple possible camera projection. Can be seen here. So here we have this plane z equals 1, and then here we have our x-axis. Here is the z-axis, and an object which is further away still lands on the same point because of this normalization that we do. We divide by the z-axis. So all the points that lie on this line are projected on the same point here on the screen, or the projection screen. Yeah, and that also shows us that we lose information, right? All those points, which are different in space, now become one on the 2D projection, right? Yeah, and this loss of information is taken advantage by optical illusions by artists, like this one, I think, from Escher. Here you can see there's a waterfall, and it dries a water mill, and then this water actually flows down. Like at every point we can see that it goes down, because it looks like this, and all of a sudden it's on top of the waterfall again. So this looks like a perpetuum mobile. But of course, it's not really possible in the real world. It's just an illusion because of the cues that the eye takes locally. right? So the eye tries to reconstruct the 3D world from just 2D, and usually it works, but here it was tricked. Yeah, so here are some more examples of optical illusions. So here we can see two lines with different arrows on the end. And when you look at it, this looks like at the near end of a cube, right? So these might be the edges of a cube, and this would be a near end. On the top, this looks like a far end of a room, for instance. If this is, for instance, the edges of the wall and the ceiling, then this might be the far end of the room. So if something is further away, it must be bigger. That's how the brain interprets it. So that's why this line looks shorter, because it seemingly is the closer one than this one. Although when you put a ruler to it, they both have exactly the same length. Right, so this basically fools the eye because of this loss of information. It tries to reconstruct the 3D world from the cues in 2D. Similar here, we have seemingly two tilted lines because of those lines, diagonal lines. They give the illusion that this is like a wall going up, and then those lines should become more narrow if they're really in parallel, and since they don't, they appear tilted outwards. But if you measure it, they are actually exactly in parallel. So here, similarly, this appears smaller than this one here because of the surrounding circles. Yeah, so this also leads us to the decomposition into pixels, right? Pixels means we sample the image. And important here is that the brain recognizes partly hidden objects, so also hidden from the grid of the point grid of the screen. So you can view what you have on the screen with the pixels, and in between you have dark lines, for instance. Then the brain interprets it as something on in front of it, and still recognizes the object which is behind. And that's also what the eye itself is doing. So the eye itself has those rods and cones, and the brain then makes a contiguous image out of it, or an object. Yeah, so how do those visual cells look like? Those photoreceptors. So let's take a look at this picture here. So here you can see a cross-section of the retina. So here you can see from the bottom there's actually light coming, and you have the light-sensitive cells here on top. Right, and here you can see the rods and cones. And the rods are those long cells, and they are sensitive to light of any wavelength. So they are the most sensitive, and they are only sensitive to brightness, not to color. And we have many more of them than we have rods. And rods are divided into three subtypes for the three different primary colors: red, green, and blue. Right. And then you can see below we have some sort of circuitry going on here. And then on the bottom, where the light comes in, we have the nerve fibers going to the brain. So the light actually has to cross the nerve fibers, then the circuitry, and then only it reaches the light-sensitive photoreceptors. Right? So these parts need to be transparent. But of course, it's not perfect. So this actually costs some sensitivity, some light sensitivity here. But as I mentioned, this is because the way that the eye was evolving as an extension of the brain. Unlike squids, some types of squids which have separately evolved eyes, where the nerve actually comes from the other side. So they are then, as a result, more light sensitive. Yeah, so what's interesting also for coding and compression is the number of rods and cones and the different numbers that we have. So the rods are approximately 120 million. They are for the bright dark vision. So we have a lot of those. Like that's like 120 megapixels. Then the cones for the color are just 6 million. And they are also concentrated in the so-called yellow spot for the color vision in daylight. So they are concentrated in our sharpest region of vision, and they are less sensitive to light but to color, and that's why they work perfect at daylight. And this different number is also important for transmission and compression purposes, as we will see. So here you can see a plot of the concentration of rods and cones. So here's the angle from the fovea. Here the fovea is the region of the sharpest vision. And you can see that in this part the cones are highly concentrated here with a blue peak. At the same position the rods basically disappear. Right? There are no rods, just cones very densely. But a little bit off, quite quickly, the cones concentration tapers off and the concentration of the rods increases, right, until we reach this maximum here. And then we have this blind spot on the nose side where all the nerve fibers go through the retina and into the brain, and that's why we have no photoreceptors here, right? So that's again a drawback of having all the nerve fibers on top of the retina. Okay, so what is actually color or light? So here you can see it. Here is the entire wavelength spectrum of electromagnetic waves starting at 10 to the 4th meter. So that's 10,000 meters. And then it goes to like 100 meter here, where you have medium wave radio. Then you go up or down to 1 meter, where you have VHF, UHF, very high frequency, ultra high frequencies, which is where you have TV transmissions and radio. Then 10 to the minus 2, so this would be 1 centimeter or a few centimeters. You have radar, microwaves, Wi-Fi. This is in this range, and altogether this leads up to visible light. So here you can see it, like here you have infrared, so everything below in frequency or above in wavelength is infrared. It's basically heat radiation. Then we have this very narrow band of visible light, and here you can see an enlargement of it. You zoom in. So visible light is around in the wavelength range between 400 nanometers and 700 nanometers, and 1 nanometer is 10 to the minus 9 meters. So here this is just below 1000 nanometer, and 1000 nanometer would be 1000 times 10 to the minus 9 is 10 to the minus 6, which is 1/1000th of a millimeter. So this is actually a tiny wavelength here. And these are actually in the order of large molecules, and that's why we can actually see color on surfaces, because the light interacts with large molecules on the surface. There are some resonances, and then the wavelength according to these resonances are absorbed, and that means the reflected light has a different spectrum, spectral shape as the incoming light, and that gives it color. So the brain interprets that as color. Above the visible light you have X-rays and ultraviolet. So first comes the ultraviolet, and these are even shorter wavelength, and they can interact with smaller molecules, like on the surface of the skin, and cause, for instance, sunburns. Or X-rays can also penetrate deeper and destroy biological molecules, and hence they are not healthy. Then we have gamma rays. Gamma rays usually come from radioactive decay or from deep space. Yeah, so coming back to the visible light range, here you can see the visible light range. To the left we have the shortest. We have 380, so this is ultraviolet already, and then it goes up here to 760 nanometers, which is the beginning of infrared. And this is just under 1,000th of a millimeter, so this should actually go here. And then you can imagine that at certain point on this wavelength spectrum we have our primary colors, right? So here you have red, here you have green, and here you have blue. And these would be basically the light-sensitive elements in a camera, the light-sensitive elements of a pixel in a camera, or a light-emitting um, display for recreating the image. Right, so here you have some given primary colors. And then the curve here shows the spectral sensitivity of the eye for daylight and for night. Right, so the blue one shows the sensitivity curve of the rods. And when you compare this to moonlight, then you can see that it's actually nicely adapted to moonlight, because the spectrum of moonlight looks basically like this. So it's like a matched filter for moonlight, which maximizes the sensitivity for dark light. Here the reddish curve is for daylight. So you can see here this curve is slightly shifted down in frequency or up in wavelength, and that corresponds nicely to the spectrum of the sun on Earth. Right? So again, the eye is adapted to this light source during the day, and here light source during the night. Yeah, and you can see it a little bit more precisely. Here the dashed line is the combined sensitivities of the three cone types for day vision, for daylight. Right? And this basically results if you combine the contributions of those three cones. The blue one, this sensitivity curve here, is enlarged by a factor of 20 to make it visible. So it's actually tiny. It's not very sensitive. And you can also see here that this red cone also has the little side lobe here in decaying slope of the blue cone. And this little side lobe here makes us distinguish violet from blue. So here in this part of the blue range we see blue, and then when we come into these wavelength ranges here, it gets a reddish hue again, so this becomes violet then. If you wouldn't have this side lobe, then basically everything would look the same color of blue, just with different intensity. So this acts almost like an additional cone, like birds, for instance, have. They have like 4 or 5 cones. We don't, because originally our ancestors were night-living creatures, little mammals like mice during the age of dinosaurs, and since they went living mostly at night, color vision was not so important, so they lost the cone here, unlike the dinosaurs or later the birds, who were always night living creatures. So this is kind of like a redeveloping additional cone here, which improves the color vision of humans. Okay, yeah, so this is from this book here. Yeah, and in this luminosity function, which we just saw, we can quantitatively see the different sensitivity of the eye for different wavelengths of light. Right? So cameras and monitors have their centers of their sensitivity of the primary color filters or the primary color dyes of the monitors at the marked locations, the arrows that I showed. And there we can see the corresponding sensitivity. So I should call this sensitivity of the eye. Right, so now we can try to make like an artificial rod out of these color sensors. The combination of eye sensitivity and some nonlinearity of monitors result in factors of the so-called luminance component Y, which we now compute, which can easily be viewed as a black-white version or dark-bright of the color image. So this is kind of like virtual rods. So here you can see the red component, the green component, and the blue component. And here are the corresponding sensitivity factors for those wavelength regions for our luminance function or the luminosity function. So this is kind of like an artificial rod, this Y output. We need this because we don't really have rod sensors in cameras. We just have red, green and blue, but nothing like the rods that the eye has. Yeah, and this becomes now part of a color transform YUV. So in order to use the different sensitivities of the eye for brightness, the luminance, and color, the chrominance, color transforms, I should call this transforms, are carried out after the camera recording or the cameras in general. The most common is YUV and is defined by the above mentioned luminance component. So here you have it. This is this formula again. And if this corresponds to the rods, we know we have 120 million rods, so very many of those, which means we need a correspondingly high number of pixels for transmission. Well, not quite the same, but a relatively higher number than for the color components. So the color components are now still missing. So now we have one component. Originally we had three components, but we don't want to come up with another three components because our goal is here to compress, right? So we already have some information in the intensity in Y. So basically we can now come up with two additional components for the color type, right? So for a good separation of luminance and chrominance, we need color components which become possibly zero when a pixel is achromatic without color, or when it's only black, white or gray. Yeah, so it was used in analog TV, which was the original goal too, in order to cause possibly few disturbances or distortions in black and white television. So when you had the original black and white video, then you wanted to have, even if you transmitted through the color system, you wanted to have the same undisturbed image on the original black and white TV sets. Yeah, so this property is obtained with the color components, which we call U and V. Color components are also called chrominance. Right, so the first one is defined as U, defined as blue minus Y. Right, and the next one is V, which is defined as red minus Y. So basically these are all the blue components, blue pixels, minus the Y component of all pixels. And same here. Yeah, so by this definition we do not get a perfect separation of the brightness and color information, but in practice it is sufficient. In the decoder we can easily recover the original using these formulas here. Blue equals U plus Y and R equals V plus Y. And here the green component, remember the green did not appear here, we just had the two weaker components, green and blue and red. So green is then reconstructed using this formula here. Yeah, and basically you can see it's all quite easy to compute, and that was important for analog TV because it was used or implemented with analog electronics, and there any computation step is kind of costly, so it needed to be as simple as possible. So here just in the transmitter just differences, but more important in the receiver just some and here just two factors and two differences. So this can also be easily written in matrix notation, right? We just take those three equations, and here we would replace y by the definition of the y, and then we get the matrix. So here we can see the matrix. So here is the familiar coefficients for y, and here for the next two rows we would get these coefficients by plugging in y into the definition above. So then we get those numbers. Yeah, and you can see here that the sum here is always 1, which means the value range of y is the same as the value range of r. And the sum of the next two rows is always 0. So when you calculate it, it's actually, they always add up to 0, each of those two rows. And that's important because if r, g, and b have the same value, then u and v will become 0 as desired. Right? So r, g, b have the same value if it's not colorful, if it's just black and white or gray. Yeah, so due to the smaller number of color-sensitive cones in the eye, the color components can now be transmitted with a smaller bandwidth, or I should say sample rate. It's almost the same, but here it means we have fewer samples, which means fewer pixels for the color components than for the luminance. Yeah, and in analog TV, U and V, the two color components, have bandwidth of about 1.3 megahertz in the PAL standard, which we have in Europe and most of the world. And the component Y uses about 5 megahertz on the transmission channel, right? Can be over the antenna or cable. It's always this bandwidth. Yeah, so in the receiver or decoder, this color transform can also be I should call this inverted or reversed by applying the inverse matrix. Right, so we have this matrix here in the encoder, then we just have the inverse matrix, bringing it on the other side in the decoder to obtain the RGB. And that's important because our display or screen expects RGB, because again, each pixel consists of those three color components. Yeah, so this leads me to this Python example. So this actually shows how it works by implementing it in a Python program. Right, so this shows the color transform. So it's shorter. So the first shows a live video from the webcam, and the other the components YUV, right? So let's take a look at this program. gedit. So here you can see it. In the beginning, I just import the necessary libraries, NumPy for the math functions, and then CV2 for video capture and display. Here I'm creating the windows that I'm using. So first I want to display the original color video coming from the camera. And here are then the three components, the luminance Y, and then the color component U and the color component V. And here I'm now generating those components in this infinite loop. So in this loop in the beginning, I'm reading a frame from the camera. Red was the binary value, which tells us if we successfully obtained a frame. And here I'm creating the Y component. So you can see I'm taking this frame from the camera and taking color component blue. So here the third index denotes the primary color, 0 means blue. So that takes basically the entire image, but only the blue component, and multiplies it with 0.114. That's our factor for blue. Then the next one, 1 means green, the green component with its corresponding factor, and here the red component with the corresponding factor. Here I'm now creating u and v according to the definitions, except that I'm now doing the normalization step here. I'm dividing the y by 255 because what comes from the camera is 8-bit unsigned integer, which means we have value range between 0 and 255. And here I'm turning those unsigned integers into floats because I multiply them with float numbers. And if I have float numbers, then OpenCV expects the value range between 0 and 1. Right, so that's why I'm dividing by 255. Same here, right? So I'm taking the green component, the blue component, getting a value range to between 0 and 1, and then subtracting this normalized y. Same here with the color component red. Then we have the u and the v component, and I display it here. So this is basically what would happen in the encoder or transmitter. So it would transmit the u, the y, u, and v. And I have this infinite loop until I press the key lowercase q. Okay, so let's try this program here in the terminal shell. So here I just executed with Python 3 because Python 3 is the newest version of Python. So let's see what happens if I start it. So here you can see the result. So here's the original video in color. Hi everybody. And here you can see the different components. Right, so here you can see the Y component, the luminance, and you can see this is pretty much like a black and white version of this color image. And then when you look at those two color components, you can see that you only see something if it's colorful. Like for instance, the wall here in the back, it's all black because there's no color to it, right? And this is how we designed the components u and v, such they are only active if there's color, right? Like here in my face or here in my shirt, that's where color is. But otherwise it's black. So even if it's white, as long as there's no color, it appears black in the color components. Right? So this shows that it actually works. So this only becomes active if we actually have something colorful, a color video. Okay, so back to the slides here. Yeah, and this also shows that the required multiplications and additions work problem-free with the whole frame without the for loops. So here I can just take the entire frame and divide or multiply or do the subtraction here. So the entire frame or the entire matrix or array is used for the complete computation. Unlike, for instance, if you would use the C programming language, here you would need 2 for loops for those indices. Yeah. So here's an example for the entire encoder-decoder chain. So let's open this example here. Copy, gedit. So here you can see it. Again, here we have this infinite loop. And let me also set the resolution here, because otherwise it would display a too big window because of my high resolution camera. Right. So here you can see actually I have 3 flags, right, which I'm using to turning on Y, U, and V. So this basically is implementing a transmission chain using the V or U, Y, U, V. And I can turn on and off the different components, and for that I'm using those different flags. Right. So here you can see is the encoder. So here's the Y component as before, here's U and V, and here's the decoder. Right, and here I'm reconstructing the Y component, not yet. So here basically I'm setting default values in case they are not transmitted. So if they are not transmitted, I need to replace the values by some default. So for the Y, it's values of 0.5 for each pixel of my image. So it's like medium gray. And for the color components, I just replace them by zeros, meaning no color. So here's the actual reconstruction. So if we have, here we take either the original or the replaced values and reconstruct B, R, and G according to our formulas. And here I'm reconstructing the frame with B, G, R. So again, 0, index 0 is blue, then we have green, and then we have red. Here I'm putting some overlay text on my window to basically describe how you can change it. So here I'm using the keys Y, U, and V to turn on and off, to toggle on and off those components. Right. And here I'm actually doing the toggling. Here with wait key, I'm basically asking the keyboard what key was pressed. And key is then the ASCII code for the key that was pressed. And here I'm just checking which it was. So if it is Y, lowercase y, then I toggle the component Y. If it was U, then I'm toggling this flag for U. And if it was V, then I'm toggling the component for V, the flag for V. So if it was true before, then it becomes false, or it was false before, then it becomes true. And if I press the key Q, lowercase q, then I break from this infinite loop and I'm ending this program here with relays of the camera and the windows. So this basically shows the contribution that those components have to the final image. So let's try. So this is actually quite instructive. Python 3. Yeah, so here you can see the original again. And now I can, well, this is actually the original and this is the reconstructed. Right now the two are identical because I'm transmitting all the components. But now I can turn on and off those different components in the transmission chain. So imagine we just have the traditional black and white TV. Then we don't have the U and V components, and I'm pressing U and V. So now you can see both are false, which means they are replaced by zeros. And all what I have left is the Y component. So now you see the black and white component of it, right? So here we just have black and white. So it still looks okay, right? Y with a high resolution, so you can see all the details, like the stripes on my shirt here. It's good enough, right? But now we can also do the opposite. Instead of transmitting Y, we just transmit the color components U and V. So first, let me turn off Y. So everything is gray now, and U and V. So now we have just U and V, and you can see it looks much less sharp, even though here I'm using the same resolution for the color components as for the Y component. But here for this video, only our cones are active. And since we only have so few cones in our retina, in our eye, it looks more blurry, right? We see much less detail because only our cones see the differences here. Now Y is basically constant 0.5, so there's no basically no information for our rods. For our rods, it all looks the same because we have the same luminosity for all the pixels. The only way the pixels differ is on the color, and the color can only be recognized by the cones, and we don't have that many. And that's why we can actually reconstruct the U and V component with much fewer pixels than Y without the eye noticing, because the eye doesn't have that much sharpness resolution for those color components. Yeah, so basically this shows why this transform is so useful, right? By just looking at U and V, we can see that we can reduce the resolution without the eye noticing it. So that allows us to save a lot of transmission bandwidth or number of pixels transmitted. Right? So this is why this reduction of transmission bandwidth to 1.3 megahertz works compared to the 5 megahertz for the Y component. Yeah. So as comparison, you could try the same with RGB. So you could say, well, maybe it works the same for RGB, but you will see it doesn't. So Python 3. Now I have the same as just RGB without the color transform. Oh, I forgot to include the size limiting. So first I need to open it with a gedit. See what happens when we have a too high a resolution camera. Then we need to reduce the resolution. So here I'm setting the resolution from the camera. So this should be better now. Oh, Python, there you go. Yeah. So here now we have a decent resolution for this demo. So again, the same as before. The reconstructor is original, but now let's say we just keep the R and turn off G and B. So now we just have the R component and you only see the reddish colors, like my blue shirt almost appears black, right? Or we can say we just have the blue component. Then we only have everything which is blue, like my shirt, right? Or the white hues of the wall and the lamp. White basically contains all colors. But you can see it's still sharp, right? We see all the details, especially when you look at green, which contains the most energy for our eye, the most intensity. You can see all the details, like the stripes on my shirt, for instance. So to the eye, it looks the same with the same sharpness, with the same resolution. So we couldn't do the same reduction and resolution for blue and green and red. Right? That's only possible if we apply the color transform, and then we can apply this resolution reduction to U and V. Okay. So that's the reason why we do the color transform, the YUV. There's also an alternative. So instead of YUV, we could also use YIQ. This is actually another color transform which is part of the American NTSC standard, and it turns out that one of those color components can even be reduced further in bandwidth. So this is how it looks like. So this is an alternative transform. Transform is shorter and is even more effective in the reduction of the bandwidth for the color components, but was more difficult to implement in analog electronics. It can only be calculated as a matrix, not by simple differences as in YUV. Therefore, mainly used in the first color color TV system. So the NTSC color television system. Yeah, and this is the transform matrix. So here you can see the Y is still the same, but then here those factors are now different. They still add up to 0, those two rows, which is important to map brightness values to color component 0. But the resulting color components are now slightly different, which you can see here. So Here it's basically like squashing and rotating the coordinate system from UV to IQ. Right. And also important is that UV and also IQ can be negative, as you can also here see. So here in the center we have 0, 0, and then we have positive and negative values. So that's different from RGB from the camera, or Y. The Y component is always positive, but U and V as well as I and Q can also be negative. And this is important for implementation, like for instance if you use integer values. For RGB you can use unsigned integers, 8-bit unsigned integer. For UV or IQ you need to use signed integer with a value range of minus 128 to plus 127. Yeah, so this is slightly rotated and squished, and as a result we can now reduce the bandwidth of Q to 0.5. So this is about 1/10 of the video bandwidth. So this is actually quite good. So it's actually kind of a pity that it didn't make it into the other color components, because in digital computations it doesn't really matter what kind of matrix you're using, but IQ is actually more efficient. So I also have a Python example in it for forward and back transform with on-off switching of the individual components. So again, let's take a look at it. Copy, first open it with an editor, gedit. So again, I need to reduce the resolution here for my camera. So here I have the YIQ transform matrix. So I just type those factors in here. And here, instead of doing the individual formulas, I'm just doing the matrix multiplication. So NP dot is doing the matrix multiplication of my frame with our transform matrix T, which I defined here. Right. So this function dot is taking it's basically taking the last index here and multiplies it, matrix multiplies it with the T. So it takes the primary colors, right? And then after this multiplication, the YIQ is of the same shape of frame, but in the last index, instead of having RGB, we have YIQ, right? So the data type didn't change, but the meaning of the last index did change. Yeah, and here I'm doing the same thing as before. So if I turn off the Y component, I replace it by 0.5, values of 0.5, so medium gray. And if the I and Q components are turned off, they are replaced by zeros. Yeah, here's the reconstruction. So we take the YIQ components, multiply them, matrix multiply them with the inverse matrix. So where's the inverse matrix? So here's the T, right, here's the inverse matrix. I'm just using the matrix inverse function here to obtain the inverse matrix. So here's the inverse. Here I'm having the overlay text again, and here is the keys for toggling the different components on and off. And here I'm ending this time with the key X, because Q is the other color component. Right, so let's execute it. Python 3. So here you can see it. So the original, here the reconstructed, everything is still on. So now turn I off. So you can now see the Q color range. So So Q is like reddish greenish, what you can see here, and turning I. Yeah, so now Y is on, now I is on, so this is kind of green-blue sort of direction. So Q on, yeah, it's kind of violet, more like violet shade, colors. So let's try that comparison with the YUV. So there you will see the axes have a slightly different meaning. So now I'm turning U off. So now I have V. So it's more greenish orange for V. And for U, you don't see that much difference. More like greenish bluish. So you can see it's quite related, but not exactly the same. Right. So in digital TV or video systems, instead of YUV, we use YCBCR. Right. That's used in digital system, usually with 8-bit resolution per component. It contains a normalization and a shift so that the values of all components are between 0 and 255, which means they are no longer negative. Right. So here you can see the resulting matrix. It's almost the same, except that we do the normalization here, such that we have 8-bit unsigned integer here in, then we get 8-bit unsigned integer out. And that's why we have also the shift by 128. So it's basically the same value, but scaled and shifted, such that everything can be done with unsigned integer 8-bit. Yeah, and once we have the color transform, we can also do the downsampling, right? We saw the I is has less resolution for the color component. So now we can do the downsampling, and there are different downsampling schemes that can be seen here. So here 444 means for 4 pixels Y, we have also 4 pixels U and 4 pixels V, right? No downsampling. Here 422 means for each row you have 4 U pixels, but only 2 U, so 4 Y pixels and only 2 U and V pixels. So horizontal downsampling by a factor of 2 for the color components. But now you can also do the downsampling vertically, and that doesn't really fit into this terminology. So here we just introduce a 0 at the end, which means we have a full set of Y pixels, and we do a downsampling horizontally and vertically for the U and V components. Right? So these gray shades mean U and V. And this is the most common version for digital video, 420. So in studios, sometimes you have 444, but 420 is the most common for digital video. Yeah, so at 420, the color components are transmitted, I should say transmitted, only every second pixel horizontally and vertically. And in this way, a color component requires 1/4 the number of pixels as the Y component, right? Factor 2 horizontally and vertically, or half horizontally and vertically. The two color components together therefore only need 1/2 of the pixel number of the Y component. Yeah, so each is 1/4, and that means both together means we just have half the number of pixels for all the color information compared to the Y component. A color image can thus be transmitted with just a 1.5-fold bitrate as the pure Y component. Right? So we just need 50% more bitrate compared to just black and white, compared to the original RGB representation, which requires 3 times as many bits as the Y component. So this is a saving by a factor of 2 without any visible quality loss, because here we took advantage of a property of the eye, that the number of cones is much less than the number of rods. Right, so factor of 2 is actually not too bad, and for basically no visible quality loss. Right, so that's it for this set of slides, and then see you in the next video. Bye bye.